one, collecting moonbeams in the morning. Curvy sticks and wooden poles, assisting you in plugging holes. Plug them holes till you see straight through to the mind's eye. Think about it, turn around and go back to the quiet sound. Jim and Dan prancing round the pool. You were the fool, and I feel sorry for you. You were the fool, but there's something you can do. You were the fool.
All right, so to continue where we left off last time, we introduced this definition of big O. We say that f of n, let f of n and g of n be two functions. And again, for our purposes, they represent the complexity of two algorithms A and B. We say that f of n is big O of g of n if there's a positive constant c and an integer n naught, such that at some point, right, so after this n naught, f of n is dominated above by g of n, right? F of n is less than or equal to c g of n, okay? Now, the idea here is that you don't want to pay attention to functions on small inputs. You want to look at them in the limit. So if you had two functions, say 175n squared plus n, and then n cubed, your intuition is to tell you that n cubed is a lot bigger. At least it grows a lot quicker. But if you only paid attention to small inputs, 0 to 100 here, you would get the misimpression that n cubed is actually better because it is lower. Remember that the y-axis is a resource measure, either time, memory, power, whatever it is. So lower is better because lower time is quicker. But if you zoomed out to about 200, say, or so, somewhere in there, you'll see that there's a crossover point. That crossover point is that n naught. That after that point, this function will never be lower than the other function, right? That n cubed is now larger, and it will always be larger going out forever, okay? So, first of all, some terminology, and then we'll get into how to actually prove this. Notationally, what we're going to do is we're going to write f of n is equal to big O of g of n. This is technically omicron, but it's exactly the same as O. So you might as well just call it O. F of n is equal to big O. That's kind of that's abuse of notation, because the thing on the left-hand side here, f, is actually a function. O of g of n, that's actually a class of functions, a set of functions. But we don't assume set notation in this course, so we're going to go ahead and go with the equals here. That's really common. It's bad notation, but it nevertheless is still common, so we'll go ahead and go with it. Once again, big O provides a relative rate of growth between these two functions as n tends towards infinity. We're not going to pay attention to small input values, right? The way to think about this is that f of n has a less than or equal to rate of growth as g of n. That's the key there, or equal to, because this is a less than or equal to definition, right? G of n, from that perspective, from the other perspective, if you look at it from g of n perspective, its growth rate is at least as big as that of f of n. Oops, let's go ahead and go a little bit further in there. There we go. All right, so it's at least, instead of strictly greater than or strictly less than, right? We're saying at least, right? They could have the same rate of growth, right? They could have the same n squared is n squared, right? Any function will have a growth rate that is equal to itself. So here's some examples, right? One example would be, say, 3n plus n, right? Clearly, if you ignore that lower order constant there, ignore the constant sitting out front, then you simplify it to n, and it is big O of n. This is the tightest possible bound. It doesn't have to be that tight. It could be looser. For example, you could still say that 3n plus 3 is big O of n squared. That's still true, because this is a less than or equal to definition, right? That's a looser bound. And of course, you can keep going, right? You can make it the other side as big as you want. You can go as n cubed or even exponential, right? Those are still loose bounds. But what is not true is if you go the other direction. If instead, for example, I said that 3 of n plus 3 is big O of log n, that is definitely not true, because log n has a much lower rate of growth than a linear function. It's certainly not true that, say, a quadratic function is big O of n, right? Those are not true, okay? It only provides a upper bound on the rate of growth, right, of a function. It's not necessarily a tight bound, okay? Tight bounds are better, and if you can get the tightest bound possible, yes, do it. For example, it would be wrong of you to say, provide an asymptotic characterization of 3n plus 3. Well, of course it's going to be order 3 n to the third, right? Well, no, provide a tight bound, as tight as possible, okay? So how do you go about proving these inclusions given the definition, right? Given two functions, f and g, how do you prove that f is equal to big O of g? Well, the first step is to write out your intuition, right? Because you need to know which one should I prove. Should I prove that f is big O, or should I prove that g is big O of f, right? Which way should I go? So over here, well, let's go ahead and take those two functions that we just mapped, or that we just plotted, and let's go ahead and write it out. F of n is going to be 175 n squared plus n, and g of n is going to be n cubed. What does our intuition tell us? Tuition, right? our intuition hopefully should tell us that n cubed is bigger. So we want to prove that f of n is big O of g of n. Okay? So we want to show that this is big O of this. Okay? That's the first step. The second step is to decide which technique you want to use. There are actually 3 different techniques. One of them that is really, really hard, one of them that's really, really easy, and then one of them that's even easier as long as you know some calculus. So what I'm going to do is I'm going to show you the first one, which is really, really hard, right? So the approach A is to find that crossover point. The largest value of n for which the 2 functions intersect. In other words, they have the same value. Over here, graphically, that means finding this intersection point where they intersect. That's going to be your n naught. And then you can say, well, or after that, what's the function value? Right, one step right after that. And you can say, well, this function is greater than this function, and that was the last point that they'll ever meet, and they're both monotone increasing functions. They will never, ever meet again, and so therefore this function is always greater than that function. Right? You are trying to find this crossover point here. Okay? So let's do that over here. Right? I want to find an n naught, find all intersection points of f and g. Okay? Well, that means for 2 functions are intersecting if the 2 functions are equal. In other words, this happens when f of n is equal to g of n. So let me write them out. 175 n squared plus n is equal to n cubed. Now all you have to do is solve for n. Right? Let me go ahead and collect everything onto one side to make it abundantly clear what we're about to do. I'm going to take 175 on 175 n squared onto the other side, along with n. And now the right-hand side is 0. Right? Now, is it easy to solve n? What's one of them that's pretty obvious up front? N is 0, right? And I can factor that out. Once I've factored out an n, what do I get? N squared minus 175 n minus 1 is equal to 0. Can you find the other 2 n's? Or, by the way, there are 3 intersection points. Why? Because this is a cubic function. Right? There are going to be 3, what do we call these things that I'm about to find? And one that we already found them. They're called roots. Right? You need to find roots. One of those roots is going to be 0. Now, what are the other 2 roots? What technique or what tool can I bring to bear? Just have to remember it from maybe middle school or high school, right? What do you find? What do you use for this?
Big X method.
The what?
Big X method.
Oh, what's the big X method? I've never heard of that.
You do that, and then you do like AC on one side and B on the other.
Oh, wow, I've never heard of that one. We usually just call it what? The quadratic formula, right?
There's 2 ways of doing it.
Oh, okay. I'm not familiar with that other way. But anyway, negative b is going to be 175 plus minus square root of b squared, so 175 squared minus 4ac. 4ac would be plus 4, right? All over 2a, which is 2, right? I don't want to do that, so I'm just going to go ahead and go over here to Wolfram Alpha and ask it to do it for me. 175 n squared it's n squared minus 175 n minus 1 roots. Right? Give me the roots of that. So there are the 2 roots. There's a plus root, minus root. And when you look at this root, it's very, very small. In fact, it's not only is it small, it is negative. Right? Is that going to be relevant for our graph? No. Because why don't we consider anything other than the first quadrant in algorithm analysis? Over here on the negative side, what does that mean? You have a negatively sized input value? Right? That doesn't make any sense. So immediately we know that that's not going to be the root that we want. But I'll go ahead and I'll write it down over here so that we don't have to recall it. And then this one is 175 and some change. So 175.005 or whatever. Right? So thank you, Wolfram Alpha, for doing my algebra, my arithmetic for me, right? There we go. We got these 2 roots. In fact, we've got these 3 roots now. Which one of these roots is the one that I'm looking for? Certainly not that one because it's not relevant to input size. 0. It's not that one. Of course they're going to intersect at 0 because any algorithm that has a 0-sized input is going to behave the same, 0 resources. Right? All of our algorithms or graphs are probably going to start out at 0 here. Right? So that's not the one I want. It's this one over here, which is that 175, excuse me, and change. That's the one I want. Okay? So this crossover point, this intersection point, is 175 and some change. Okay? So all we need to do is take the next integer value. Why don't we use this one directly, by the way? Remember, input sizes. That's what we're modeling here. There's an input size of 175 elements. There's an input size of 176 elements. But is there an input size of 175.005 elements? No, that doesn't make any sense. So, for n naught being not 175 and change, but 176, the next integer value. For n naught being 176, then f of n is less than or equal to g of n. Right? For all n naught, or for all n, excuse me, greater than or equal to n naught, where n naught has just been computed up here. What happened to my c? My c here ends up being 1. And that's what this technique is doing. You're having to, remember the definition here? The definition is that you have to find c and n naught. In other words, when you've got a pair there, what you're doing is you're fixing one of them to be 1. Right? You're fixing c to be 1, and then you're finding this other one. There are actually an infinite number of pairs for which this will work. You just have to find one pair of them. And one technique for doing that is to fix one of them to be 1 and then go and find the other one. And that's what we just did in this first technique here. All right, so one technical thing that you have to do, is that you still have to show this inequality. So for example, if I plugged in 176 for f and g respectively, then you'll get some values here. You'll show that that this one is greater than this one right here, right? And then this follows from that because the reasoning is that this is the last crossover point, right? That worked out because I made sure that there were no lower order terms. What if I gave you something like this? What if f of n is 45n to the 5th minus 3n cubed plus 4n minus 3. And g of n is, I don't know, something even funkier. 75n to the 9th plus 7n squared minus 2. Right? Do you want to set up that inequality and have a degree 9 polynomial? How many roots are there going to be now? 9, right? So who wants to do that? Who wants to solve for all? In fact, do you even know how to? We've got that quadratic formula, but that works because your polynomials are small. Degree 3 polynomial has actually several different cases. Degree 4, even degree polynomials, I think you can reduce it down to the quadratic equation, but odd number polynomials, good luck, right? You're going to be doing some interpolation methods there. No, 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 no. I don't want to do that. That's why I characterize this technique as the hardest one, right? Again, basically you are fixing C1 or C to be 1 or something like that. And then you're finding n naught, the greatest, that's the largest point where the two functions intersect. In other words, you're finding roots. This is only easy if finding the roots is easy. In other words, if you come up with a nice, well-behaved example that the roots are easy to find, right? So instead, what we're going to do is we're going to focus on technique B, which is much, much easier, right? It's just the opposite. Basically, what you're doing is you're setting n naught to be 1, and then you're finding C. right? Remember that you have to find both of those, or at least one pair that works. So all we're going to do is set up an inequality and make the function bigger and bigger and bigger until it matches g of n. And like I said, that basically you are fixing n naught and you're finding c. Graphically, what does it look like? Let's come back over here. All right, there are the two functions, right? Normally I would want to find this intersection point. What I'm going to do is I'm going to manipulate one of the functions, though. Let's see, what do I want to do? Make it bigger and bigger and bigger. Yeah, let's say, let's see. Let me take this and also plot it, but I'm going to multiply it by some value here, 2 times, right? So let's take a look and see what that looks like now. I'm plotting all 3. Oh, you can't plot all 3? Come on. Why not? I asked you to plot. Fine. Is there, no, it's right there. Oh, I see. There, thank you. Yes. I can't believe it's that pedantic about it, but whatever. All right, so there are the 2 original functions down there. And then there's my other function that's multiplied by a scalar value 2. Does that multiplying by a constant value change the rate of growth of a function? No, right? Because the derivative of a constant value is 0. No growth rate there at all. But what have I done here to this function? Right? I've pushed this intersection point back to somewhere over here. Maybe I did it too much. Let's go ahead and go with 1.125. Let's try that. All right. That's still too much. It doesn't have to be much. I guess 0.5. There we go. All right, so there's the intersection point originally. What I've done by multiplying it by that small constant is I've pushed the intersection point back to somewhere over here, right? Right? Yeah, it's still above. I'm not sure where it is. But anyway, by multiplying this, you're pushing the intersection point back. Multiply it again, right? Multiply it by some other value, 2.5 now, right? Multiply it again by 5.0. And what you're doing is you're progressively pushing this intersection point back and back and back until, in fact, maybe I should do this with n cubed. Let's try it with n cubed instead, times n cubed. There we go. Twice n cubed. There we go. We can see the intersection point right there right now. All right? Well, what happens if I push it back even further? Let's say, let's demonstrate this for 1.5. Let's demonstrate this for, say, 2. And then let's demonstrate this for 3. 3n cubed. There we go. You're pushing the intersection point back further again, until you get all the way to n not being 0. At that point, however many times you've multiplied it, 1.5, 3.5, 3, 2, 3, whatever, that ends up being your c right there. That 3 ends up being your c if that's all it takes. Now visually, that you can see what it's doing is it's pushing that intersection point back. It's even easier algebraically. Right? Let me show you how to actually do it. Right? What I'm going to do is I'm going to set up my f of n, right, to be whatever it is, 175 n squared plus n. Right? We want to show that this is less than or equal to, in a series of inequalities here, c n cubed. Right? For all n, or let's say for all n greater than or equal to 0, there's my n naught. I've fixed my n naught to be 0. And I'm trying to find my c here. Right? That's what we want it to eventually look like. All right, how do I make this function bigger? As we've already seen, you can multiply it by a constant. But you can also multiply it by a variable. What if I just took this one right here? Is it true that n is less than or equal to n squared for all n greater than or equal to 0? Is that true? Absolutely. Is it true for negative numbers too? Yeah, but all we're dealing with are positive numbers because of input sizes. So this is less than or equal to 175 n squared plus n squared for all n greater than or equal to 0. Right? Well, now that's equal to 176 n squared. Okay? Does it look like this yet? It kind of looks like that. I've got a c out front. I've got one single term, but it is not cubed. It is squared. Right? Well, make it bigger again. Less than or equal to 175 and cubed. Is that true for all integers? Careful. What if n were negative 5? Is that true? Absolutely not. This would end up being positive. This would end up being negative, and the inequality would not hold. However, do we deal with negatively sized inputs? Nope. So, for all n greater than or equal to 0, as long as you put in that caveat, this ends up being true. So, for c being 176 and n not being, n not being 0, the inequality holds. Right? No finding roots at all. All you have to do is make this bigger and bigger and bigger until it looks like g of n over here. This is equal to c g of n. For c being 176. All right? Eerily similar to that n naught being 175 and then 176. That's because I set it up this way so that everything would work out nice and easy. Right? So again, you set up an inequality and simply make it bigger and bigger and bigger until it matches c of n. This is a much easier technique. All you have to do is make it bigger. You know how to make things bigger. Be careful though. Be careful. The inequalities must hold for all specific n's values, right? In other words, if it doesn't hold for negative values, fine. But if it doesn't hold for 0, all right, go over 1 to 1. Now does it hold? It doesn't hold there either. All right, go over to 2. All right, that works just as well. We'll see an example of that later on here. Finally, the one that I'm going to cover the least is technique C, where you set up a limit. And I'm only going to cover this once, and we'll ignore it. If you don't know calculus, that's fine. But if you have calculus, it requires calculus, right? Then it's really, really easy, okay? Let's come over here and set up a limit. I'm going to state it first. If I take f of n and g of n, and I set up a ratio between them, and then I take a limit as n tends towards infinity, right? One of three things is going to happen. First of all, it could converge down to 0. Now, if it's converging to 0, that means that the denominator is growing way faster than the numerator, because this is getting bigger and bigger and bigger and bigger, right? This one is staying the same, or maybe it's getting big, but just not as big as this one, meaning that you're converging down to 0. That means that f of n is big O of g of n. Okay? The other thing that could happen is that it could converge to some constant greater than 0. Now, if that happens, that means that the growth rate of these two things are canceling each other out. Right? It's basically like one big 1 right here with some c out front here. Right? They're converging onto the same values. If that happens, then f of n is big O of g of n, and g of n is big O of f of n. In other words, they have the same rate of growth. Now, if we were doing this in, say, in 235 or 310 or something like that, a higher course, I would call this big theta, right? But I don't want too many Greek letters, right? These are Greek, right? Yeah. I only want to deal with omicron, or O here in this case, okay? All right, so another thing could happen. It could diverge off to infinity. That means the thing on the top, the numerator, is growing way faster than the thing on the bottom, because this entire thing is getting bigger and bigger and bigger and bigger. Right? That means that g of n is order of f of n. Right? That's because the numerator here is growing. The numerator is growing faster and faster and faster. So g of n is clearly smaller. Okay. Doing this with our one example, and we're only going to do one example here because we don't assume calculus. The limit as n tends towards infinity of 175 n squared plus n all over n cubed, right, is equal to, algebraically, I could split this up. And then I could say that the sum of limits is equal to the limit of sums. Right? So this is actually going to be two limits as n tends towards infinity of 175 n squared all over n cubed, plus a second limit as n tends towards infinity of n over n cubed. Okay? Some simplifications here algebraically. N squared cancels with n cubed, and so I get the limit as 175 divided by n tends towards infinity. Before we look at that second one, you tell me, how is this going to behave? It goes down to 0 because you have a monotone increasing function on the denominator and a constant function up top. You're in what I call calculus obvious land, right? And this is going to be 0. If you were in a calculus class, or maybe, and definitely if you were in a like an analysis class, you would have to show an epsilon delta proof of this. You don't have to show that here because you're in obvious land. Now, what about that second one? N will cancel with 3 there, so limit as n tends towards infinity of 1 over n squared. Now it's even faster growing towards or converging down to 0. Right? So once again, you are in obvious land, and so 0 is your limit. By this theorem here, that means that f of n is order g of n, just as we've proved now 3 times. Okay? That's the limit method. And as long as you've got some calculus under your belt, that's going to be way easier, because you can use a whole different set of tools, like L'Hopital's law, and any sort of information you can use about first derivatives and stuff like that. All right, so that is if you've got calculus. Some limits are obvious. Using some other techniques like L'Hopital's rule, et cetera, you can bring those to bear. We're going to get some more practice here, but before we do that, let's go ahead and consider categories of functions. Okay? So categories of functions. One of them is going to be constants, right? Order 1, right? If you're just writing a piece of code that is a formula expression, right? A plus B minus 3, right? That is going to take a constant number of operations, and therefore it's going to be order 1, right? What's a little bit higher than that? What's one obvious one that we started out with? N. So we call those linear, order n, right? But what about between those two? Is there something sandwiched between? Yeah, logarithmic, right? You can have order log n. Where have we seen that? Oh, so where have we seen examples of each one of these? Formula, calculations, right? What about logarithmic? What's an example of that? It's going to be seared into your brain by the end of the year, hopefully. It's also it's a very basic step to many other algorithms. Binary search, right? Binary search is going to be logarithmic, right? That's why it's better than linear search, which is, of course, where we've seen linear search, right? What would be slightly higher than that? What's bigger than linear? Quadratic, right? It's going to be order n squared, right? Any degree polynomial. This is quadratic. And where have we seen something like this? Naive algorithms such as insertion sort, right? Selection sort, right? A bad linked list iteration, right? That's what started us all out, right? Where we gave this motivating demonstration where it ends up being, if you want to do this for 1 billion elements, it's going to take you 3 seconds for an array-based list, but it would take you, what? 20 years, because this is quadratic. Quadratic is not acceptable, right? Thankfully, there's something between linear and quadratic. We call it quasi-linear, that is almost linear, right? And it's going to be order, let's do it like this. It's going to be n log n, right? So, fast sorting algorithms, like say quick sort or merge sort. If you haven't seen those, that's fine. We'll go ahead and review them here shortly, probably on Wednesday, actually, right? Because we're also going to look at algorithm analysis with respect to recursive algorithms, which we have not yet done, right? So why is it quasi? Well, it's almost linear except for this annoying little log factor over here. But as we've seen, log factors are almost nothing, right? They grow, in fact, their growth rate is diminishing, 1 over n, right? So we might as well forget this log factor over here because it's almost linear, right? Which is very acceptable, right? You can go higher still, of course, cubic, right? We haven't done anything cubic yet, but say matrix operations, multiplication. That's the most common one. If you just do a naive matrix multiplication, it's going to be quadratic. If you do fast matrix multiplication, there's a lower bound of like order 2 to the, or n to the 2.37 or something like that. Wagner's algorithm, I think it is. No, it's not Wagner. I forget what it's called. But anyway, you can generalize this for any polynomial, right? Any polynomial is going to be any n to the k, for k being constant, right? For constant k. For constant k. But as we've already seen, we're way out of, for constant k, sorry. There we go, now it's fixed, right? But as we've already seen, anything quadratic and above is pretty much no-go, right? Why? Because of this demonstration here, right? Something that's linear is going to far surpass anything that's quadratic here. 20 years is not acceptable on our big data of only 1 billion elements, right? So pretty much you're in the realm of theoretical analysis at this point because none of these things are going to be of practical use, right? Now, if you want to go even further, you'd have, say, exponential, which is 2 to the n, right? And not all exponents are equal, right? In other words, 2 to the n is big O of 3 to the n, right? In other words, it's just a different base, but 3 to the n is not equal to order 2 to the n, right? There, that's how you write it. Come on. There, that's how you write it. 3 to the n is not big O of 2 to the n. In other words, if you have just a slightly larger base in your exponent, that is so much bigger than any other base that's smaller than it, right? You can go even further, right, if you want to. Super exponential functions like n, what do we call this? What is this function right here? Factorial, right? Or some people call it the gamma function, right? These would probably come in if you're doing something combinatorial. For example, subsets. The set of all subsets is called the power set. How big is it? 2 to the n, because you can either leave something in there or you can put it in. Something that is super exponential, n factorial, is going to be arrangements. If you've got 10 people, how many ways are there of arranging them in a row to take a picture of them, right? 10 factorial, right? These are not, how many ways are there of shuffling a deck of cards? 52 factorial. These are nowhere, I mean, you wouldn't be able to make these computations within the lifetime of the universe, much less your lifetime, right? So no way are these at all acceptable on reasonably sized inputs, right? But even within your lifetime, quadratics are not acceptable either, okay? All right, so with the rest of our time, let's go ahead and look at a couple of exercises here. A couple of exercises examples, right? And to do that, I'm just going to pull up an old assignment here, right? And let's just go ahead and do some of them. This one is too trivial maybe, but let's go ahead and start out easy, right? 2 to the 2.5 n and g of n is n. Right? So hopefully this one is really, really easy to you too. First of all, which technique do you want to use? Do you want to use the hard one? Do you want to use the easy one? Or do you want to use calculus? I'm not going to use calculus. So let's do the easy one, right? So we want to show that 2.5 n is less than or equal to some c sub n because we're pulling in g over here. Well, guess what? You're already done, right? It is less than or equal to 2.5 n. So for n being, or sorry, n not being 0 and c being 2.5. Remember, it doesn't have to be an integer on c. Let's go up to the definition here, right? There is a positive constant c. C doesn't have to be an integer, but n naught does have to be an integer because we are dealing with input sizes on n. So for c being 2.5, we're done, right? We've shown that f of n is big O of g of n. You could actually go the other direction too, right? Because they of course have the same rate of growth, right? But we won't do that because it's too simple, right? Let's say, all right, this one is a little bit more difficult. No, this is not difficult at all. That's easy too. Here we go. Here's something involving logs, right? We want to show that this is big O of, or actually no, sorry. Let's go with 64n is big O of n log n. Right? So in other words, this is my f right here, and this is my g. Okay? All right, so let's set up our inequality. N log of 64n. Right? And I need to show ... that this is less than or equal to some c n log n. Okay? All right. Well, to start out with, let's go ahead and try to get rid of that 64. To do this, it's just simple algebra, and algebra plus logarithm identities. If you've got log of a, b, right, a times b, how can you break that up? Log of a plus log of b, right? And so when I break that up, don't forget that n out front there, I get log of 64 plus log of n. Right? All right. Implicitly, what's our base here? 2, right? So what is log base 2 of 64? 8's too much, right? That 8's 255 or 256, isn't it? Maybe I'm wrong. 2 times 2. So 2, that gives me 4. 4 is 16. 16, it's 6, right? 6, right. And 6. I always remember that if you go 2 to the 8th, that's the ASCII text table, right? Because there are 8 bits in every ASCII text value, 8 bits in a byte, and that gives you values ranging from 0 to 255. So there's 6 plus log of n. Algebraically, what I'm going to do is I'm going to move these around. So this is equal to n log n plus 6n. All right? Move this down to give myself some more room here. All of that was just equalities. Now let's make it an inequality. This is less than or equal to what? Well, log of n plus, how can I make this other one bigger so that it looks kind of like this? Multiply it by log n. Right? Careful. For all n greater than or equal to 0. What's log of 0? Yeah, it's going to go where? Down to negative infinity. For us, however, that's going to be undefined. All right? This is where you have to be careful. No, that's not true. All right? Is it true for 1? Well, what happens when you plug in 1 over here? You get 6, right? 6 up here. What happens when you plug in 1 right here? 0, right? So is 6 less than or equal to 0? Because that's what the entire thing would end up being. Forget about your 6n over here. Log of 1 would end up being 0. Is that true? Nope. Keep trying. Is it true for 2? 6 times 2 is 12. Right? 6 times 2 times, what's log of 2? 1. Is that less than or equal to? Yep. And after that point, it doesn't matter, you can go 3, 4, 5, or whatever, right? Then it's going to be greater than or equal to, right? So be careful, right? Your ends have to make sense, okay, for this technique to work. At this point, though, we are done because combining these two things gives me 7n log n. And so for n not being 2 and c being 7, we've shown this inequality. Right? So when you're involved with logs, when you're involved with exponentials, right, be careful because not everything is going to be clear-cut like it was, say, on the super easy one. Right? Okay. Here's 2 more. Right? Here's one. n 2 to the n is big O of 3 to the n. Okay. All right, let's set up our inequality. n 2 to the n is less than or equal to ... We want this to eventually look like c 3 to the n. All right. Okay. What can we do? Generally, if we've got a function here of n and a function here of n, right, I want to combine them somehow to get down to one function, right? So is the following true? 2 to the n times 2 to the n. In other words, is n less than or equal to 2 to the n? Yeah. For what n? 0? 0? 0 over here would give me 1. Yeah, that works. Is n less than or equal to 2 to the n for n being 1? Yep, that works. Is it for being 2? Yep, that works. So, for n greater than or equal to 0. Okay. What is that equal to? Is it 4n?
4 to the n.
Oh yeah, that's what you meant. I don't know. Let's ask Wolfram Alpha. 2 to the n times 2 to the n is equal to 4 to the n? Question mark. And it is true, right? Good. But what have we done? Is that ever going to look like this? 4 to the n is way too big, right? All right, so let's back it up. Right? You can make things bigger and bigger and bigger, but you can't make them too big because then you've shot over your goal over here. Right? You've overshot your goal. So let's go ahead and go back. All right? All right. Okay. I really want to fold that n into 2 to the n. How can I do that? Or more precisely, what could I make n to make it look like this? What could I do with, what about the following? Well, here, 1.5 to the n times 2 to the n. What is that equal to? 3 to the n, right? That would work, but is that inequality true? What about for n being 0? Right? 0 and then 1.5, that works. N is equal to 1. 1 and then is less than 1.5, that works. What about n is 2? 2 less than or equal to, what's 1.5 squared? I think it's 2.25. Right? Looks like it works to me. Right? So for all n greater than or equal to 0, which is equal to 3n. So for n being n not being 0 and c being 1.5 or c being 1 in this case, sorry, excuse me, we've shown this inequality. Right? All you have to do is be a little bit clever about how you manipulate your inequalities here. Right? You just have to make sure that you're not overshooting your target. Okay. By the way, another dead end would have been to say, oh well, what if it's I don't know, 2, right? is that wouldn't work because if you replace this with just a scalar, right, that's not going to be true when n is 3, right? Okay. All right, one last one, and this will be maybe the most complicated one that we do. I want to show that log of n factorial is big O of n log n. Now wait a second. We just said that n factorial is super exponential, right? That's just that's about as big as you can get, at least for sensible algorithm analysis, right? So how could it be n log n? Well, if you take the log of something very, very large, you get something very, very reasonable, right? So let's set up our inequality here. Log of n factorial. Right? Okay, this is going to come up later in some analysis that we do at the end of the course. Right? What is that equal to? That's n times n minus 1 times n minus 2 times dot 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 times 3 times 2 times 1. All right? Now look at each individual one of these, and what's the highest order term here? Which one of these is the largest? N, hopefully, right? So what if I were to replace each one of these with n? N, 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 right? Okay? That certainly is going to be less than or equal to log of n times n times n dot 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 n, where we've got n of these n's. What is that equal to now? If you go n times, these are multiplications, n times n times n times n times, what do you have? N to the n. Once again, pull out your memory and tell me what you can do with exponents inside of a logarithm. Pull them out front. Guess what we have here? N log n. Right? So, for c being 1, and be careful, n not being what? Is this well defined for 0? Nope. Is it well defined for 1? Yes. Right? Actually, 1, 0. Yeah, that's fine. Right? I was just thinking over here. If you put in 1 over here, what's 1 factorial? It's 1. So what's log of 1? 0. So 1 times log of 1 is going to be 0, so 0 is less than or equal to 0. That works. Right? Okay. 2, 1. Yeah, that would still work too. Right? How about 3? 3 factorial ends up being 6, and then this ends up being 3 and 3. Yeah, that's going to work there. Right? All right. By the way, what about the other way around? You can show it using Stirling's formula. But we're not going to get into Stirling's formula. All right, so several examples. You just need to have some reasonable practice at doing this stuff. But otherwise, once again, 3 different techniques. The one that I would say that you should go with if you ever need to is technique B here, because it is the easiest. Just make it bigger and bigger and bigger. What we're going to do next time is we're going to pivot to the analysis of recursive algorithms. Okay? And we'll look at that on Wednesday.